Uh, hey, it now, I just clicked that and it says recording. I tell you what, well, there's no, but if it's recording, they can watch it later when she posts it. I'm going to go ahead and give my talk, and I'll talk to you later, okay? Thank you. Thank you so much for calling. Yeah, that's what I'll do. Yeah. Okay. Thanks. Ta-ta. Okay, students. Sorry for the problem. I have 8:45, but I started here and I don't think I was recording, but I believe I am now. And today's Wednesday, the 22nd, and the situation is snafu. That happens with computers, as you know. This is the last day of class, and I want to have a review for you guys. Your final should be posted this morning, and I'm giving you a review today. And these are things that you must decide whenever you do a thermo problem. You must decide on the model. And the two main models that we use are the tables in the back of your book, and they're well, what I meant to say was the two main models are the tables in the back of your book and the ideal gas law. Those are your two main models. Well, there's actually several ideal gas laws and several laws that are derived from the ideal gas laws. But those are your two main models. And then there's the compressibility model, computer models, there's physical models. An example of those are on page 36 and 37 in your book. And then I was going to talk to you about the different processes. There are a lot more than that. There's also the polytropic process. There's reversible process. And irreversible. There is isenthalpic process. There is isentropic process. And I have a feeling there's more than that. Well, there's an infinite number of processes, really. There's an infinite number of polytropic processes. There's an infinite number of adiabatic processes. There's an infinite number of isochoric processes and the others. So there's lots of different processes and probably some that I forgot. Now on when it comes to units, we have SI units and we have English units. And we use these two different unit systems. And you know, you've encountered those throughout our course. There's, what is this, kilojoules and kilowatts and cubic meters, and this one here is BTUs per pound mass, cubic feet. Yeah. You've got to decide which system are we in. Now, if you're in the SI system, then don't go to the back of the book in the English tables and use those values. If you're using English units, if the problem uses pounds and BTUs, don't go to the back of the book and use SI units in the back of the book, meters cubed and per kilogram and all that. That'll really mess things up. So you have to make sure you're in one or the other. You have to know what processes you're dealing with. You have to know what model you're using. And then your device sketch. There's different devices. Like, for instance, there's the piston cylinder. You know how that goes. It's sort of a deal like this, okay? Piston cylinder. And a turbine, for instance. See, that's a piston cylinder. Now, if you had a turbine, the symbol for a turbine that's the device sketch. But there's a lot of others. There's compressors. I'm running out of space here. There's pumps, there's boilers, there's pipelines, there's heat exchangers. There are some of the things that we've talked about. There's throttles. Here's a little room right here. I'll put a throttle in here. See, that's a throttle. There's what do you know about throttles? Throttles are isenthalpic. Throttles are isenthalpic. There's okay, what am I trying to think of now? No, that's not a throttle. That's wrong. Now, the symbol for a throttle is a device like that. I had that wrong, but I got it right. What I was thinking about was a nozzle. Now, a nozzle is not isenthalpic. A throttle is. A throttle is isenthalpic, but a nozzle is not. Now, a nozzle, that's the device sketch for a nozzle. And you can put a lot of information on your device sketch. So whenever you do a problem in my class, you must know what the model is, the process, the units you're using, the device sketch. I ran out of room there, so here, let me erase that and we'll talk about some other things that you have to decide whenever you do a thermal problem. You have to decide whether to do a PV or a TS. And I think for some of our work, I wanted you to do both. We started off, all we knew about was PV diagrams. And then later on, I forget which chapter, I think it might have been chapter 6, we learned about TS diagrams. Let me look and see what chapter that was. Let's see here. We definitely had them in chapter 7. Yeah, we had them in chapter 6. Oh, what about chapter 5? Chapter 5. I might have had them in chapter 5. I see a PV diagram in chapter 5. I don't know. I don't think there's any TS diagrams. But in chapter 6, we started learning about TS diagrams. And see, they come in two different styles because you can have a actual gas or you can have an ideal gas. An actual gas will have a vapor dome. There we go. Whereas an ideal gas will not have a vapor dome. So you have to decide on that, whether you're going to go PV or TS diagrams. What else do we need to decide? Well, then we studied cycles. Oh, well, now first though, there's the first and second laws. The first and second laws of thermodynamics. Did you know there's two forms of each of those? One for control masses and one for control volumes. Did I mention that? You've got to decide whether you have a control mass or a control volume. Actually, there's 3 versions of both of these, because you can have steady state or you can have a transient process. On the list of processes that I have, I forgot transients. But control volume problem can be steady state or it can be transient. And there's different versions of the first and second law. Now I put that under content. I have a nice, if you pull up the content page there, you'll see all of those first and second laws for control masses and for control volumes. Well, what else? Then there's cycles. We started studying cycles, and I tell you what we've studied. We've studied Rankine cycle. We've studied refrigeration. We've studied the refrigeration cycle. We've studied the one that they didn't record on YouTube, the diesel cycle, the Otto cycle, Stirling cycle. Now, am I forgetting any? I might be forgetting some, I don't know. Rankine, yeah, I'm forgetting one. I'm forgetting the an important cycle. Which one was it that I'm forgetting? the Carnot cycle. Ran out of room. Let's put it over here someplace. Now, we've spent a lot of time on all of those. And you have to know what they are. Now, the Rankine cycle has two adiabats and two isobars. The Rankine cycle has two adiabats and two isobars. The Carnot cycle has two adiabats and two isotherms. Refrigeration cycle, it has well, it's got two isobars. It's got an isentrope. And it has an isenthalp. Diesel cycle. What's it got? Well, let's see. It's got two adiabats. Running out of room here, but diesel cycle has two adiabats. It has one isobar and one isochore. What about the Otto cycle? Amen. Two adiabats and two isochores. I wish I had some students here, but I don't. I somehow pushed the wrong button here. I don't have anybody watching this now, but you could watch it on YouTube if we get it put on YouTube. Stirling, what does that have? It's got the two, I gotta stop and think now. Two isotherms, I know that. I believe it has two isotherms. And two isotherms and two isochores. See, they're all different. They're all different. Now, these here are all dealing with air. Diesel, Otto, Stirling. Well, not necessarily, because Stirling can have other things besides air. I don't remember if I gave you a Stirling with helium, but I think I did. I think I gave you a Stirling problem with helium. Don't necessarily have to have air, but diesel and Otto are air. Whereas these here, the Rankine, well, it can be anything. But no, I take that back. They usually use H2O. They use water for the Rankine. Yeah. It's the Carnot that can use anything. The Rankine's water, the refrigeration can use a bunch of things. Some kind of refrigerant. When I was a kid, we had a refrigerator with ammonia, but they use these other refrigerants now. Okay, well, there's a little review, and if I only had some students, I could ask you to ask me a question there, but I don't, because something happened. We don't have this thing hooked up right. But we're going to go ahead and do some review problems anyway. This is a review day. And what we're going to do now is another thing you have to do when you do your thermal problems, you have to know which equations to use. Now we know there's the first and second laws. We know there's the ideal gas laws, but we have other laws, and that's what we're going to talk about now. So let me erase all this, and we're going to talk about what laws you can use and when you can use them. This is a review day. It's Wednesday. All right, now this is a sample problem I just made up, and we'll go through it and maybe we'll learn something. Maybe you already know this. Suppose you started off with a pressure at state 1 of 2,000 kilopascals, and specific volume at state 1. Here, let's give you the temperature instead. So temperature at state 1 of 350 degrees Celsius. And then you're going to have a process. Here we go. We're going to have a process. And it will be a polytropic process. To state 2. Now, state 2 is going to have 3,000 kilopascals and T2 of 800 degrees Celsius. Okay, now we're going to we're going to find a lot of things. We're going to plot it up on a PV or a TS diagram. We're going to find the polytropic constant. See, there's going to be one of those little n things. They call that the polytropic constant. Okay, well, let's find that first. Now, the way you find that is you go, well, we're going to need V1. You can't find it without that and V2. So go with me to your book and help me find 2,000 kilopascals and 350 C. Might take you a while of snooping around to find that. But I'll tell you where it is. (2,000 kilopascals, 350 C). I found it. And the little V1 is 0.13857. I am on table B.1.3. Now, while we're at it, let me go ahead and get U1. Now, I didn't tell you this, but this is a piston cylinder situation. We're going to have a piston cylinder situation. And U1 is 2859.81. Okay. And I don't know if you need H1, but it wouldn't hurt. We'll write it down. H1 is 3136.96. Did I get that right? Yeah. And then little s1 is 6.9562. Okay. Now, let's go to 3,000 kilopascals and 800. So help me find that 3,000 kilopascals, 800. It looks to me like V2 is 0.16414. And U2 is 3,653.58. I wonder if I got that right. Yeah. And H2 is 4146. And S2 is 7.9862. Okay. Now we're going to try to find this little n. Well, here's the way to do it. P1 V1 to the n is equal to P2 V2 to the n. And see, we know P1 and V1. And we know P2 and V2. So it's just algebra. It's just algebra. I think I'm going to spare you the algebra, and I'll tell you what I got. I plugged those in, and I did my algebra, and I got an n equal to minus 2.3943. Okay. Now what we're talking about now is an example of different equations to use. And here's one of the equations that we use in this class. This equation has a name. It's called the polytropic equation. Now, my question to you guys is, do you have to have an ideal gas to use this equation? It's called the polytropic equation. This little n here is called the polytropic constant. And if I could get this thing to work, but I can't, see, I don't have anybody listening to me because somehow I fouled up. But I would ask you, I would say Stuart or Spencer or one of you wonderful students there, like for instance, I'll tell you, I would call on maybe Roxana or Aubrey or Bear or Parker or Megan. I'd call on one of you guys and I'd ask you, can you use this? Does it have to be an ideal gas in order to use that? And I'd say you have a 50-50 chance of getting this right. Can you use it with an ideal gas? Well, the answer is yes. You can definitely use it with an ideal gas. But see, we don't have an ideal gas. We're dealing with H2O. Remember we looked in the table, where's my table number? Did I write? Yeah, table B.1.3. That's a water table. We're doing a problem with water, and water is just not an ideal gas. But can we use this equation? And the answer is, ta-da, yes. This equation works with anything. If it's a polytropic process, it doesn't have to be an ideal gas. It can be anything. Okay. And if you know this, and you know this, and you know this, and you know this, and you took algebra in school, you can solve for n, and that's what you get. Okay, great. Well, then what? Well, let's solve for something else. What if you wanted to know a little w? Now, see, little w is the work per mass, right? It's work per mass. Now, how do you do that? Well, there's an equation for it. Let me see if I can write it down. I need some room here. I need some room. I hate to erase all my good stuff, but you guys, this is going to be recorded, and you're going to have all those numbers there. You're going to have all those numbers written down, because you all take good notes of my wonderful lectures, whether I got them online or not. Okay, now here's the equation for little w. There's an equation that I taught you guys. In fact, we derived it from scratch. I derived that equation for you. I'm pretty sure I did. I'm trying to think. Did I? Yes, I did. I derived that equation. What I did was I used the idea that work per mass is the integral of P dV. It's the area under your PV graph. And I used this equation here. I use these two equations. They do not depend on an ideal gas. This works whether you have an ideal gas or not. This works whether you have an ideal gas or not. And I showed you, using these two, I came up with this lovely equation here. So you don't have to have an ideal gas to use that equation. Isn't that nice? Now, P2 is 3,000 kilopascals, and V2 is 0.16414, and P1 is 2,000, and V1 is 0.138 0.57. And N turns out to be negative 2.3943. Now, I didn't go through the details, but you guys took algebra, and you can plug that in and get it. And you can plug this in and get it. Again, I don't think I'm going to go through the agonizing algebraic details, but here's what I got when I got through. I got 63.43 kilojoules per kilogram. Here, I'll shut up for a minute in case somebody would like to plug all that stuff in and see if they don't get that. Go ahead and see if you can get that. Well, okay, I gave some of you time to get that work per mass. Now, here's one of those equations. You know, when you do these problems, you have to know which equations to use and when you can use them. We don't have an ideal gas. We're dealing with water. But you can use that because that's a polytropic equation, and it's perfectly good. Okay, and we got the work per mass. Now let's find delta U. Now there's different equations you can use to get delta U. Now one of them goes like this. That equation there only works if you have an ideal gas. See, we have all these equations, but you have to know when to use them. That one we can't use on this problem because it's water. Water does not behave like an ideal gas. So we can't use that. So if you wanted to find delta U, which is what they call the specific internal energy, how would you go about it? Well, you just subtract. Look, here's U1, here's U2. We can subtract them. We just got these out of the table. Can't use ideal gas stuff, but you can use the tables. Okay, I'm going to do that. Here goes. I'm going to subtract those, get my delta U. 3653. I'm going to subtract 2859. And I am getting delta U is 793.77 kilojoules per kilogram. Wonder if that's what I got when I did this before. And no, I got a different number. No, that's what I got. Yeah, that's good. Now we can get the heat transfer. See, we have delta U and we have little w. We're going to get the heat transfer now. But I need some room. Let me say goodbye to some of this because I need the room here. This is a closed or control mass. See, we're dealing with a piston cylinder. Is that how you spell cylinder? Yeah. See, it's a control mass. And there's a very lovely equation that goes like this. It's the first law of thermodynamics for control masses. And see what we know what this is and we know what this is, so we can solve for the heat transfer. All right, well, let's do it. Let's see, delta U is 793.77. Work is 63.43. So, hey, we can solve for Q. Let me do it. Let's see what I get here. Plus 63.43. I got 857.2 kilojoules per kilogram. Is that what I got before? Little q. Yeah, that's what I got. Now, I wish I had more room to write here. We need to do our device sketches and our PV diagram. See, I always do those way at the beginning. I'm kind of doing this backwards. But I'm going to make some room here. I need the room, so we're just gonna make the room. Here we go. And we're going to do the device sketch. All right, here's state one. Okay. Here's state one. And here's state two. Now notice the pressure went up, but what about the volume? The volume went down. I probably shouldn't have erased it. Little v1 is 0.13857. We got that from the tables. We just looked it up. Little v2 is 0.16414. The volume actually went up. And the pressure went up. Here, let's put some weight on here. There you go. So there's our state one and state two. What about the temperature? Well, it got hotter. it got hotter. You know what? I get the feeling there's got to be a heat transfer into that. Well, what it is it's steam. It's superheated vapor water. It's steam. You got H2O in here. You got steam and somebody transferred some heat into it. I guess they put it on the stove. Put that piston cylinder on the stove, and well, it'll go up even when they put some weight on. It'll still go up. Okay. Now we can get the heat transfer because delta U will equal Q minus W. Delta U is 793.77. Work per mass is 63.43. Hey, we can solve for the heat transfer. Here we go. I guess I already did that, huh? There it is. Yeah, we already did it. That heat transfer in is 857.2 kilojoules per kilogram. You put it on the stove, heat's transferred in. Well, it pushes the piston up, even with the added weight on it. Well, good. You know what we've gotten so far? Let's see. So far, we've gotten N, we've gotten little w, we've gotten little q. What else are we going to get? I don't know. Well, we'll think about it. Let's do our PV and TS diagram, shall we? Okay. Where am I going to do them is the question. Yeah, there's some room right in here. Let me make some room and we'll do our TS and PV diagrams. All right, here we go. PV diagram. Well, now it's water, so it's going to have one of these. TS. It's going to have one of these. Okay, now we know we're in superheated vapor. And I'll tell you where 350 is. Let me get some red here. I happen to know the top of this hill is, I think it's 374 Celsius. 350 kind of does this. This is red. That's the 350 degrees Celsius isotherm. But see, we're out there in the superheated vapor. See, this is superheated vapor. We're out there in superheated vapor at 2000, which is maybe down here someplace. So that puts me right there, state one. Okay, we got state one there, that's good. Now where's state two? Ooh, it's 800 Celsius. Well, that's way above the vapor dome, you know, the 800's up here someplace. The 800 is up there someplace. And what is the pressure there? 3,000. Well, see, 3,000 would be in here someplace. So that puts you right about there, state two. Yeah. Now, wait a minute. Something bad happened. I got to redo this because our volume got bigger. It didn't get smaller. It got bigger. So How am I going to do that? Don't know yet. Let me think about it. Let me doctor this up a little bit here. Okay. Let me hug this one down here a little closer like that. State one. I know the volume's getting bigger. It's kind of going like that. The volume's getting bigger, and the 800 is doing this. There it is. There's the 800. There's state one, there's state two. The volume got bigger. The pressure got bigger. Something like that. All right, now what does the TS diagram look like? Well, we'll try to draw it too. Well, 800's up here high. It's above the vapor dome. But 350 is lower. There's the 350. But I don't know what the S is doing. That 800 is supposed to be here. I don't know whether the specific entropy is getting bigger or smaller, but I can find out. Now I had those up there and I erased them. There is an equation that goes like this that we know and love. Do you guys remember this equation? It's a lovely equation, but that only works for ideal gases. We can't use it here. This is water. If you want the change in specific entropy, you can't use that equation. You have to know when to use your different equations. That one you can't use. We don't have an ideal gas. But see, we have the values. I erased them. But delta S is equal to S2 minus S1. And you can look those up. Now, I did that. And S2 is oh, gee, I got lost here just a minute. Let me shop around. It looks like it's 6.9562. But now what's S1? Well, don't know. But I can look it up. I have a table here. Let me just go back and get it. See, I ran out of room and I erased the S1. But at 2,000 kilopascals, and 350 C, S1 is, that was S1. S1 was 6.9562. It's S2 that I want to put right here. See, S2 is at 3,000 kilopascals and 800 C, and it is 7.9862. I had those on the board earlier and I erased them to make room. Okay, now if you subtract those, you'll get your delta S. Here goes. 7.9862 minus 6.9562. Well, I got a positive 1.03. It's positive. You know what that means? It means it got bigger. So that means you go to the right. So if this is state 1, then state 2 kind of angles off to the right because the specific entropy got bigger. So there you have it. We've done device sketch. We've done some equations. We've done some PV and TS diagrams. And what this problem was dealing with water in a polytropic process, going from one state to another. And here, if I had my students, and if I had this hooked up to where I had my students, which I don't have anybody, it's just me here this morning. It's kind of like the National Football League playing with no spectators. It's no fun without the spectators. But I understand, if I heard right, they're going to do some games with no spectators. Okay, well, that was fun. And here I would ask for any questions that you may have. But I tell you what, let's do a different problem. Let's do another one with water. I'm going to erase all this stuff. We're going to do another problem with water. But this one here, why don't we do it a little different? Why don't we go from here to here for 2,000 to 3,000, but not necessarily that temperature. And we'll have a different N here. And instead of polytropic process, we'll start at the same place here. But this time, let's have, what do they call that? Isentropic. We're going to do an isentropic process. Now, what does that mean? That means that delta S is 0. Well, the one we just did, delta S was not 0. I forget what it was. We just did it a minute ago, but it wasn't 0. And the one we did a little while ago had a polytropic constant of minus 2 point something. Well, how would you do this? If you knew the starting, now the stuff we had before is still good. When you look this up in the superheated vapor table, you still have that. You might look up, let me repeat these. I lost them, but you have them in your notes. I got 285981, and S1 is, and we did that, S1 is 6.9562. You can find these on table, gee, I just erased the table number. B dot something dot something. Here, let me look it up. It's water. It's in the superheated vapor. And it is it looks like B.1.3. Yeah, that's right. This is table B.1.3. You can get all of those. But see, we got a different process this time. This process is isentrope. We didn't have an isentrope last time. See, isentrope is delta S is 0. Last time we had delta S was positive something. I forget what it was now. But if you're taking notes, you know what it was. But this time it's going to be 0. I can tell you this. I can tell you what little s2 is. It's the same as little s1. You know what? It's 6.9562, isn't it? Yeah, because delta S is 0. It's an isentrope. That's what an isentrope is. It's when your change in specific entropy is 0. Okay. Well, so what? Well, you could go to your table and interpolate and get little v2 and little u2 from the tables. But to get them, you have to interpolate. You got to go to your table at 3000 and you look up to 6.95. Well, it's in between some numbers. You can find it. It's in between 400 and 450. Okay. Well, you go back there and you interpolate. To get these numbers, you have to interpolate. Now, we've done that a whole bunch of times. You guys have seen me interpolate a whole bunch of times before. I think what I'm going to do is I'll just leave that with you, let you do that. I'm going to just give you the answers. Here's what I think the answers are. Hey, we should have a T2 also. See, the T1 was 350, but T2 is not going to be 350. Don't know what it is, but you can interpolate it. Here's what I got. I got 410.8. Looking at the table, I can see where it's got to be. It's got to be between 400 and 450, and it is. It's 410.8. And little v2, I'll tell you what that is. When you interpolate, I'm getting 0.10120. Can you read my writing? Let me write bigger. 0.10120. And little h2, I'm getting 2951.71. Now, if you're really serious about this class, and I think you guys are, or you wouldn't have come this far with me, you should verify that T2. Make sure I got that right, and that V2 and that U2. And I know you can do it. Okay, now after you do all that, now we can answer questions like, well, what is the work? What is the Q? What is the delta S? Well, if it's an isentrope, delta S is 0. That's no problem. And if it's an isentrope, We're going to say it's a reversible adiabat. So there is no Q. Okay, great. So therefore, delta U is equal to Q minus W. And if Q is 0, we can get the work per mass. So delta U is 2951.71 minus 2859.81. That's equal to minus W. And you guys all know how to subtract. That's not even algebra. That's more like, I don't know, 5th grade, maybe 4th grade. I'm confident you guys can do that. And if you do, we can get the work per mass. Here goes. To 2951.71 minus 2859.81. Ta-da. Did you get, now be careful, watch out, there is a little algebra there, you know what? Because I'm coming up with a negative. It's a negative 91.9 kilojoules per kilogram. Well, look, the volume got smaller. It's compressing. We know the work of compression is negative, so yeah. So we got the work Q is 0, delta S is 0. So we got the work per mass. We got a lot. Now let's do our device sketches and our PV and TS diagrams. Here goes. All right, well, we're going to do that now. Device sketches. Well, where am I going to do that? I need some room here. Let me sacrifice some of this stuff here. And we're going to put our device sketch in now. Now, what did we say happens? The volume gets smaller. Ooh, the volume gets smaller. Here's state 1. Here's state 2. The volume gets smaller. So what? What about the pressure? Ooh, the pressure went up. You know what? That almost makes sense. If somebody puts a heavy weight on that, that's going to push it down. The volume will get smaller. I like it. What about the temperature? Ooh, the temperature went up. Well, that makes sense too. Did you know when you compress things, the pressure goes up? Yeah, that makes sense. But what about the heat transfer? There isn't any. Remember, this is an adiabat. It's a reversible adiabat. So they must have insulated this. Put an insulating layer of some kind of insulation. Like my attic has fiberglass insulation. It works pretty good. Pack that with fiberglass so there's no heat going in or out. Now the temperature goes up, but there's no heat transfer in or out with the environment. But because you're compressing it, the temperature goes up. Okay, great. Well, what does I think we're done. We have our new temperatures, our new volumes, our specific volumes. Let's do our PV and TS diagrams. Okay. Well, there's a little room right here. Let's do a PV diagram. Now remember, we're dealing with water, so yeah, we got to do that, right? And what do we say the volume does? It gets smaller. We're out here in superheated vapor at 2,000 kilopascals. We're going up to 3,000. So, and the volume gets smaller. There's state 1. There's state 2. Ta-da, that's what it looks like. And the work now, well, the work is the area underneath this PV diagram. And because it's compression, it's negative, 91 something. Well, let's do the TS diagram. Here we go. TS diagram. We're out here in the superheated vapor at 350. Well, actually 350 is up here pretty high up. 350. So we're right here. And we're going to what, 410? That's above here. 410's up here, so but it's straight up. There's state 1, there's state 2. The entropy doesn't change. It's 6.9562 the whole time because it's an what do they call that? Isentrope. No, yeah, it's an isentrope. So there's your PV and TS diagrams. All right. Well, let's do one more thing together, I think. This is a review session today. I need to get on Blackboard and give an announcement that this will be put on YouTube when my daughter gets home. But we need to do a problem with air, which we'll treat as an ideal gas. Ordinarily, I would say, do you have any questions on this? But since I don't have any students logged on to this, we're out of luck. So let me erase all this and we'll do a problem with air, and then I think we're just going to quit. That'll be enough for today. We've had a pretty good time together. This is our last session. You've got your homework, or I think you got homework and an exam to do for me. And I'll get those graded. This is just Wednesday. I'm sure I can get that done by Monday night, turned in. Okay, now we're going to do a polytropic process with air. We're going to treat it like an ideal gas. We're going to go a polytropic process with N equals 2. And we're going to go from 200 kilopascals, 300 K, polytropic process to 500 kilopascals. That's the plan. And we want to do all of our wonderful things. We want to do our device sketches. It's a piston cylinder again. See, on this review, I'm kind of going back to earlier chapters because we've just recently been doing control volume chapters. but your final exam is going to have stuff from all June and July, kind of the whole course there. So I thought this would be a good review for us. You've got air in a polytropic process, n is equal to 2. That's called your polytropic constant. And the first thing we're going to find is what T2 is. Now here's this equation. This equation you can use now. It is a ideal gas equation. We weren't able to use it on that previous problem that we just did with the water because water is not an ideal gas. This equation can only be used with ideal gases. In fact, it's got to be an ideal gas with a polytropic process. But that's what we have. We have air. We can treat that as an ideal gas. Well, here, let's put in our numbers now. Let's see. Oh, we don't know what T2 is, but T1 is 300. P2 is 500. P1 is 200. And N is 2. So you go N minus 1 over N. We can do that. Again, why don't I shut up for a minute and some of you can plug that in and get it. Well, that's probably not enough time, but I did that. You might have had enough time. I came out with 474.3 Kelvin. 474.3 Kelvin. Let's put that on a PV diagram while we're at it. These really should be done early in your problem, not when you get done. Now there's no vapor dome now. See, it's air. So what you could have is a couple of isotherms. You could have a 300. There's your 300. And you could have the 473. So this could be the 474.3, and this one could be the 300. Okay, and N is equal to 2. Now you're starting off at 200 kilopascals. And you're going to 500. I don't know if it's that far up, probably in here someplace. 500 kilopascals. And so, yeah, there you have it. There's your state 1. There's your state 2. Yeah, that looks pretty good. Now, if I had time, I would do the TS diagram also. Maybe later we can finish that off. But we want to get the work done. Now, it looks kind of like the work's going to be negative to me, but let's see if we can do that. Now, here we go. We're going to do the work per mass. Now, this equation works for ideal gases too. That equation works for water, it works for ideal gases. Now, since we have an ideal gas, we can be lazy and write this as RT2 minus RT1 all over 1 minus n. Okay. We weren't able to do that with the problem we just did with the water because P2V2 is not equal to RT2 for water because water is not an ideal gas. But air is. So we can get our little W here. It's going to be, for air, it's 0.287 kilojoules per kilogram Kelvin times 470, 4.3 minus 300 Kelvin. We can get our work done. I did that. And I got minus 50 kilojoules per kilogram. I'll give you guys a tiny minute. Some of you might want to verify that. Okay, there's your work per mass on a polytropic process with air, with the polytropic constant equal to 2. Came out work is negative. Why is it negative? Because it's compression. We really need the device sketches to show you that, don't we? Wonder if I have room to put device sketches in there. Hey, we'll make room. We'll make room. We'll put the device sketches in here. Okay, here's state 1. And here's state 2. Now what's happening? The volume's getting smaller. It's compression. The volume's getting smaller. Yeah. Okay, what about the pressure? Ooh, the pressure's going, well, you know, that kind of makes sense. If you put a heavy weight on there, the volume will get smaller. What about the temperature? Ooh, it got hotter. That kind of makes sense too. When you compress an ideal gas or an actual gas, they still get hotter when you compress them for sure. All right, well, there's state 1 and then there's state 2. And see, what you're supposed to do is write all the facts down here. I'm kind of lazy. I didn't put all the facts and run out of room. But here they are. This is 200 kilopascals, 300 K, where this one here is 500 kilopascals and 474.3 K. Yeah, great. Now, what about the heat transfer? Well, we have this equation here. This is a control mass. We can get the heat transfer because we know the work. Let me circle that. We know the work. Delta U is not a problem. That's equal to CV delta T. Now, CV for air is 0.717. And the delta T would be the 474.3 minus 300 K. And that's going to equal Q minus W. Okay, great. Make a little room here. We're going to get the heat transfer. And now watch it. You've got a minus sign here in your first law, but this work per mass is also minus. You've got two minuses. That makes a plus. So algebra students, you've got two minuses there. And I solved this, and I've got a value for Q. And I got Q turns out to be a positive 75 kilojoules per kilogram. Here, I'll give you a minute. Why don't you plug that in? Plug that in with this minus 50 for the little w, and see if I did that right. Well, I think I did it right. Actually, I got 74.97, but I rounded it off to 75. That's pretty dang close. So here, let's draw that. We have a heat transfer in, of 75. Now there's two reasons why this thing got hot. Remember, it was 300K. That's just kind of a real warm day in Oklahoma, isn't it? 300K. What is 300K? Just out of curiosity, let's see if I can figure that out. It's 27 Celsius. How do you convert Celsius? You multiply by 9/5, and you add 32, don't you? That's 81 degrees. You started off with 81 degrees. You put a weight on there, and you put a heat transfer in of 75, and it got hotter. It went up to 474.3. What is that? Let me see what that is, just out of curiosity. Holy cow. I got a humongous number there of 394 degrees Fahrenheit. Really hot. It got hot. Well, there's two reasons why it got hot. One is you put a weight on there and that compressed it, and that makes things hot. And the other is you have a heat transfer in. Okay, well, great. We got the heat transfer, we got the work per mass. That's the heat transfer per mass. We got the work per mass. What about the change in entropy? Well, we could do that too. Yeah, we could do that too. Now here, let me make a little room here someplace, and we'll do that. What if I ask you that? Yeah, we'll make some room here, and we'll get the change in entropy. Now we have an equation for the change in entropy. It goes like this. Actually, we have two equations. They should give you the same answer. We have another one that goes like this. Now, these are supposed to give you the same answer. It'd be good for you to practice that. I don't know if we ever got the specific volumes though, but we could get them if you know P and V or P and T. You can get the specific volumes, and we know P and T. We got the T. Yeah, you could do both of those. That'd be a good check to make sure you feel good about those equations. Now these are nice equations. When are they good? They are good if you have an ideal gas. Well, we do. We have air, so it's okay. Well, here, never mind that bottom one. You can do that for fun. Let's plug this in and see what it is. Now, C sub P for air, I happen to know by heart, is like that. Okay, there's your numbers. I'll give you a minute. You plug those in, and we're going to get the change in entropy. Here we go. Okay, I know I didn't give you enough time there, but I'll tell you what I got. I got 0.1969. And the units are kilojoules per kilogram Kelvin. And what we need to do now is to draw our TS diagram. So here, let's do that. Now we're going from 300K to, what is it, 474 or something? Yeah. Here's the 474 or 474.3 degrees Kelvin. And here's the 300 degrees Kelvin. And N is equal to 2, and we solve that. And here's state 1. And we got to change an entropy. It's a positive, so it kind of goes in here like that. There's state 2. Entropy goes to the right because the change in entropy is positive. Okay, well, great. Now that's with an N equals to 2. This was not an isentropic problem. It would be interesting to do this problem to start with 200 kilopascals, 300K, and go to 500 kilopascals with an isentrope. Now, if you did that, there couldn't be any heat going in. See, isentropic process is adiabatic and reversible, right? So the temperature would be smaller. It would be smaller, and the TS diagram would go straight up. It'd be interesting. It would go like this. It'd go straight up. But the temperature here it would be smaller. Why don't we call it T with a little s underneath it to denote constant entropy. We could find out what that temperature would be if you had an isentropic process. Let's do that, and then I think we'll quit. I've had enough fun for the semester. I just need a little room. Here's some room right here. So we've tried to show you device sketches, equations, diagrams. Look here now, T2 over T1 equals P2 over P1. If it's an isentrope, then this will be 1.4 minus 1 all over 1.4. And we have the P2, it's 500. We have the P1, it's 200. What we don't have is the T2. Here, we have all of these things here. But see, the 1.4 is only good if it's an isentrope. Do you understand? See, what we had was n equals 2. We solved this with 2 minus 1 over 2. If you put in a 1.4, what you're talking about is an isentrope. And what you'll get, if you'll do this, for those of you that are just super students, you can plug that in and you'll get a temperature of 389.8. You see this temperature right here? It's cooler. It's 389.8 Kelvin. How come it's cooler? Because you didn't have any heat transfer in. That's why. It still got hotter because you put a weight on it. But it didn't get as hot because you don't have any heat transfer. This would be your isentrope. Now let's see what that looks like on a PV diagram, and then I want to quit. Need a little room here someplace. I'll let you digest that for just a minute, and then we'll do the PV diagram. Now, if anybody just kind of woke up from a daydream, we're reviewing. We did a polytropic process with air when n is equal to 2. And we plotted it, but I erased it. Now let me put that back here. Let me put my PV diagram back here because I want to show you something. Now we're not going to put a vapor dome on this because it's air and we don't have a vapor dome. It doesn't condense to liquefied. At room temperatures and these kind of pressures, it doesn't turn into a liquid. But we have a 300 K, and we have I erased it, but it was 474. 474.3 K, and our process went like this. From state 1 to state 2. This is when your polytropic constant is 2. Now, when your polytropic constant is 1.4, it goes like this. This is n equal 1.4. I don't know, can you read that? Maybe. But see, this is going to the same temperature or same pressure here. It's going to a pressure of 500. It starts at a pressure of 200 and it goes to 500. It's just these are different processes. Here's your state. I don't know, you want to call it state 2S maybe for constant entropy. Can you read my writing? That's a 1.4. This process here, don't get confused. This process here is n equals 2. This process here is n equals 1.4. See, this is the adiabat. And I'll tell you a fascinating thing. Here's your adiabat. Right here. No heat transfer at all. The temperature is going to be smaller. Here, I'll draw it through here. The temperature through here is smaller. You know what it is? It's the 389.8 Kelvin. That's a little bit cooler than 474, isn't it? A little bit cooler. Why is it cooler? Because on the adiabat, you don't have this heat transfer going in, making it hotter. See, when n equals 2, you've got a heat transfer going in, it makes it hotter. Temperature goes up to 474. If there's no heat transfer going in, it'll be cooler. It still heats up because you're putting this weight on it. Now, here's the thing I wanted to show you guys. Anything on this side of your adiabat, the heat transfer is positive. Anything on this side of the adiabat, anything on that side of the adiabat, the heat transfer is negative. If you're right smack dab on the adiabat, if you're on the adiabat, the heat transfer is 0. Between a heat transfer being positive and a heat transfer being negative, obviously in between there, it's the heat transfer is 0. Okay, well, I wish I could have talked to you. I'm going to get on Blackboard and try to explain what happened here. And I wish you well. Have fun on your homework and your exam. Bye-bye for now.